most of that spot in the circuit in the tape-out class. The tape-out class is mostly geared towards analog listening and RF, so maybe more analog-ish. There's another digital tape-out class offered by Professor Chris Tang, but that class is more only the tool and you actually tape out the digital circuits. As far as I know, they tape out like processor, okay, some kind of digital processor. So you'll be coding RTL code and you go through the flow and you do the tape out, which is very different from analog, right? Because analog you need to get to individual devices and do sort of a manual layout and then so you understand the whole process. Okay, so let me just take a quick poll. If the tape-out class is offered in the summer, so I'm gonna do two, right? So one will be in the summer, the other one is in the fall. Okay, and what would be your interest in the availability to take that class during that time? Okay, so this is a tape-out class.
What number is this? 505?
505, yeah. So this is 505. All right, so summer or fall. Okay, so you just need to raise your hand, that you have interest and availability to, because you need both, right? In the interest and also availability to actually take it. Okay, so if you're out for the summer term for the tape-out class, please raise your hand. So this is summer class. Okay, so now move to the fourth class. Fall class. Oh, actually very close. 10. So this is not really helping. I was hoping that there's some dominant factors. For those, actually, I think they're quite non-overlap. I don't see that there's a group of people raise their hand. So let me ask, how come you only take, so those who select for fall, why is the reason you cannot select for summer? What's the reason you cannot?
Probably because we get an
Internship? Any other good reason? Okay, I told the department that may be quite a good reason. Okay, for the same reason, those who vote for summer, why can't you vote for fall? Those who just raise your hand for the fall semester, for the summer session, looks like you don't vote for the fall semester, and what's the reason? Like, weather is too cold, I don't like it, my brain only function when, any reason? No reason?
That might be the last semester of semester. So that might be the last semester of some students.
Oh, last semester, okay. Okay, yeah, so that will actually go to the, another question. There are master students here, right? Okay. Right now, by default, master student program is 2 years, right? 2 years, 4 semesters. In some rare situations, some students, they want to squeeze everything into 3 semesters, even though we don't suggest, we don't recommend, because you want to, as you can see, there's a lot of material in each class, right? So if you cramp everything into a short period of time, sometimes, it just kind of increase the difficulty for you to digest and learn the material. Okay, but that being said, I still want to get a poll. So is there master students here? So the 2 questions. So MS students. So if you are not master student, you don't need to participate in this vote. Okay, so there's a 4 semester. And there's a 3 semester. Okay, so I'm just take a poll right here. You plan to finish your master program within 4 semesters? Please raise your hand. Okay. Anyone want to take for 3 semesters? too. All right. This is I like, yeah. So there's more difference. Okay. Yeah, we do suggest for 4 semester models because you know all the class that we kind of release or design was meant for 4 semester curriculum. Okay. All right. Yep.
Is there a plan to do a bring up course after the tape out for
Yes.
validation?
Yes. Okay, so here's a new agenda that we're trying to push. The reason why I'm asking you this summer and fall, and I don't ask you spring, is because we want your trip to come back. So that you can measure your trip in the spring. So this is a whole set of class. So either we do summer or fall, and if you get to tape out, right? So we're gonna leave for about 3 months for the trip to be fabricated. And then the last semester of your master program, if you're a PhD, probably wouldn't make too much difference anyway. But particularly for master students, then this can be really helpful, right? Because then you get to test the actual chip that you did. So that was exactly the plan. So it's very important. We think that this is very important for your education purpose. And in fact, you know, for those of you who are looking for a job, you know, more and more they're asking this kind of experience. Did you have TEFL experience? Now, in the past, they understand that, okay, probably most of those TEFL experience was restricted to PhD students. If you are circuit PhD students, they understand that, okay, you must have some TEFL experience. Okay, not so much for the master or undergrad. Okay, but in the past few years, I would say 2 years, 3 years, more and more universities start to offer this TEFL class, including USC. So we did the same thing. So you get to tape out. It's just that we did not offer the measurement class. So now we are changing this. So in the past, it's that, oh, after this semester, when the chips come back, the chip will just deliver back to you, and then you need to work with the instructor to have some special arrangement. Okay, so maybe we need to find some lab space at USC. So you go there in some weird time slot to do this, right? But now we try to make it more formal, right? So we have a whole set of the actual measurement class. And there we can also teach you how to, for example, how to design the PCB board. Because a lot of times you need to design the PCB to actually test your own chip. So there will be a lot of material go along with that, right? But it is our intention to formalize everything so you get the full experience all the way through, right? From the beginning to the end. Okay. So that's kind of the right now. As you can imagine, this is a big investment on the school. We have really a lot of infrastructure we need to do the tape out. You know how expensive it is.
Everybody gets a chip. Every student
Oh
gets
yeah,
a
yeah.
Huh?
You will get the chip.
Oh,
You tape out, you get the chip.
oh.
The department is gonna absorb the cost. So you are not paying extra tuition for this. Somebody need to pay. We are working out with the school that, okay, yeah, you need to pay for the benefit of the students. Yeah. So there's everything that you can gain from this kind of experience. But we do need the enrollment. If let's say we plan out better, you understand all this efforts will take us lots and lots of time to even design the material, to even figure out how we can set up the environment so that you guys can go there and do the layout. There will be a lot of burning on our end, okay? Not just instructor, TAs, schools. So we really don't want to go into the situation where we go, okay, pump up, we prepare everything, and say, okay, how many guys are gonna register for the class? Not that many, then it's a waste of time. So all this, and then just so that you know, right now, if we don't get more than 10 students, we cannot offer the class. Right, I mentioned in the beginning of this semester. So right now the school at the moment are very sensitive to this financial spending. So every time we create a class, it's a lot of cost. You see that there are a lot of staff behind the scene you don't see, right? The website, everything. So all this go along with this. So we need to. So we are borderline. So like if this is really the enrollment that we are looking at, we are at the borderline that we cannot even offer this class. Right. So of course this is just one class. There may be other classes, but I kind of think that majority of the students who will take this that tape-out class will be the one coming from here. Okay, it will be 536A and 631 class. Okay, yeah, so that's kind of the hope. Any other suggestions? So the hope is that we do tape-out either in the summer or fall. In the following spring, you continue to take the measurement class. So you measure your own children.
So what will we benefit from it if I graduate on December 2026? So fall, my last semester. What do you recommend?
You will still get to the if you actually do take this class, you still can claim that you participate in the real tape-out. Because even that is very I wouldn't say trauma, but it's it is a process. So you went through all that process. You still can be proud and then say that I have taken this class, 505 class. That's real tape-out. You can talk about what technology you know and all that. Yeah, it's just that you won't get the chance to really measure it. Yeah. Which one can argue is a big pity, right? Because after you spend all these efforts and you don't even get to measure it, whether that actually works in that. So, yes.
So is the 505 tape-out use the MPW or real business?
I think usually it's MPW tape-out. Once in a while, we may get some donation from the company. So for example, Apple is interested in donating some their internal tape-out. So that's an example. So if we get enough interest, maybe we will work with Apple to say, oh yeah, we have enough students on campus are interested in this, and you can see why they want to do this, right? They want to recruit you, right? So if we have this class, we're gonna keep all this transparent to them. They can even see your class performance in that class. They may be able to even see your layout. Oh, you know what? Oh, these 5 guys, looks like they can do pretty good layout. Okay, so think about what they may do. Okay, so there's some interest and also some logic there. I think that we may be able to benefit from. But it's a two-way process, right? So no matter how we are excited to set up this, if the students are okay, then it's just okay. Then that becomes something optional. Okay. So I'll let you know the development. We should have some decision by the end of this semester. So you should get to know.
Can we do the poll again? Since that you explained everything and there are some people coming after you took the poll.
Oh, okay. Sure. So let's do the poll again. Specifically on the tape-out class. If you are interested and available to take in the summer session, please raise your hand. Okay, so one more. 10. Okay, what about in the fall semester? By the way, you can double vote here, so it's not mutually exclusive. No. Oh, so 4 actually slightly more. think it might be in fall. Yeah, I personally think that fall might make more sense. The only trouble is that
It should still come like in the fall.
yeah, because you see,
in December.
yeah, because when you tape out in fall, then the chip may come back next year in March.
March, and you have to do the PCB.
Yeah, so in the beginning you can learn about how to do PCB and all that, right? So in the beginning, but then it's just that then your testing time will be somewhat squeezed. Yeah, so that will be the downside of the fall. But I can understand, especially for the master students, because you guys all may take some opportunity in the internship. So the fall may make some sense. Yeah. Any more question?
If the tape-out class is the summer, we probably have to graduate in 3 semesters. Yeah, because our last semester is just taking 1 classes, but if we're taking summer, we'll be only taking 3 semesters to finish the whole programs. They just trying to explain to people who don't want to go to the fall.
Sir, you say that if you take the summer session, you would graduate within 3 semesters?
Yeah.
This is a 4-credit class, right?
Yeah, because we actually taking 7 classes, but each classes, it won't become a full-time student. We have to at least to enroll in 2 classes. Yeah.
So last semester is only 1 class. We have to take only 1 class.
Okay, but if you take only 1 class, you're saying you cannot be considered as a full.
Yeah.
Full
Only the last semesters, the 4 semesters, you can just be considered to be a full-time.
Oh, so you're saying you will be forced to graduate within 3?
Yeah,
So
yeah,
basically
yeah.
by default.
Yeah.
Interesting. I see. Okay, so 4 will be more normal, basically, if you take the full semester. Okay, that's actually a good point.
Isn't it used to be summer anyways?
Hmm?
Isn't the 505 offered in summer?
In the
always?
past, yeah, in the past, yeah. Yeah, we've been offering in the summer. Actually, because of that, that's why I know a lot of students, they say that, oh, actually, I wish to take this class, but I need to do internship. Yeah, so that's why I'm asking department to reconsider to maybe offer it also in the fall, for that reason, yeah. Yeah, otherwise you're right, so far summer works pretty well, especially for PhD students. They are around anyways. Yeah. Okay. Okay, that's good. Just need to report back. Okay, so we're almost done with this variability, right? So last week we did this analysis on this basically current mirror, right? Just to see how this current variation, right? The normalized current variation in percentage, will be a function of the beta variation and also the threshold voltage variation, right? And then obviously we realized that it's inverse proportional to the VD set, right, of these current mirrors. So that's the design parameters that you can do to improve the variation. Okay, so it turns out that it's probably pretty much applicable to all kind of device. Okay, so obviously we talk about this threshold voltage, right? So we say that okay, this AVT is process dependent factor, right? So you have this AVT divided by square root of area, right? But then if you look at all the other factors like a beta factor, right? So beta is the mobility and W over L, right? Turns out that they are the same thing. Still inverse proportional to square root of area. Bipolar, same thing. Inverse proportional to square root of area. Resistors, same thing. right? Inverse proportion is real area, and capacitor, same thing. So everybody basically come down to, because all this averaging effect, it just come down to, but note that all these are normalized, okay? They are all normalized, so it's a ratio. Okay? It just come down to how large of the area you are willing to do, right? So talk about this the tape-out class, right? So you're gonna experiment this, you decide what size that you want to do. Then you're gonna have a different amount of the variation. Okay, so that's really the bottom line. And for this reason alone, remember I told you about this technology scaling, right? The digital guy usually they can enjoy the area being shrink and shrink and shrink. The analog guy cannot. This is the reason, right? So your area will ultimately determine what's the variation, right? And unfortunately, a lot of times we cannot tolerate this as much. Okay. So you're gonna have some exercise through the homework. We'll give you some variation, and then you can experience. I think that might be homework 2. Homework 1, I don't think you have this. Probably homework 2. You're gonna start to see this, and you can get some feeling of. Interesting. How come they kicked me out? Okay, so those are the numbers. All those variability, you would launch. So in SPICE, we have to launch this so-called Monte Carlo simulation. Okay. So whenever you hear that, oh, you need to do Monte Carlo simulation, that's usually what it will capture. Okay, so the foundry, they will provide some kind of variation range. Okay, statistics basically. Okay, of all these transistors, capacitor, resistor, right? So that's the foundry's job. So they're gonna give us the model, statistical model. As long as you run this Monte Carlo simulation, it will basically create a circuit as if this is a chip you get back from the foundry. Okay, if you do a Monte Carlo for 100 runs, 100 different runs, it's as if 100 different chips you're gonna receive. Okay, so this is what the ultimate yield analysis, right? So you can simulate all these Monte Carlo, and if that's 99 out of the 100 Monte Carlo runs, you omit the spec, then what's your yield? 99%. 99% you're gonna get a working chip, right? At just 1%, you're gonna fall out of the spec. Okay, unfortunately, the SPICE model that we're gonna give you in this class won't be able to allow you to run the Monte Carlo. Okay, is that good news or bad news? Depends. Depends on what angle you're thinking. All this Monte Carlo simulation takes a lot of time. Okay, so. So what I'm gonna do is that in the class project, what I'm gonna do, I'm gonna ask you just to hand calculation. Okay, so you do the hand calculation to find out what's the variation to justify the sizing that you are choosing. Okay, any question? Okay, so that's usually how I cover the technology. But since 2 years ago, I add this supplement material. The reason is quite simple, because you look at the mainstream technology, it's pretty much in the FinFET, right? The FinFET. Yes.
Was this posted on Brightspace?
It should. I haven't. Okay, so I'll do that maybe during the short break. Okay. Yeah, so I will upload all this. a lot of this material, thanks to Dr. Elvin Lok, he actually came here to give a seminar last semester, I think. And in a couple years ago, I invited him to give a guest lecture here in my class, in this class. Of course, right now he's very busy, so he cannot do it. Fortunately, I was able to steal his slides. Okay. He has tons and tons of slides, but I kind of adapt from his slides and then make it more analog mixing on the material. He obviously talk about a lot of processy stuff. I suppose you don't have interest. Certainly, I don't have interest. I'm not doing any processing, so I kind of modify it so that the analog circuit people would kind of need to know. Okay. Would be good to know, I should say. And don't worry, I'm not gonna test you any of this in the final exam. Yeah, this is only for the benefit of your future potential projects. Okay. In fact, some of my students are actually working on this FinFET, so I suggest them to come here, but they didn't come. So this is a FinFET technology. All right, so let's start from the planar to the FinFET. I think I covered this a little bit, right, in 536A. So this is a planar device, so you have NMOS and PMOS, right? And the PMOS is being that, you're sitting within the unwheel, right? Remember that, right? So usually I show you the cross sections. In the FinFET, you see this U shape, right? So this is called fin, 1 fin, 2 fin, 3 fin. Right, remember I say that the channel is basically encapsulated into the 3 sides, right? The ceiling and the 2 wall. So that's what you're seeing. Okay, so you have a NMOS, and you have a PMOS. PMOS is same thing, you sit within the unwheel, right? So and then you have the body tie, somewhere, right? Just like a planar. Your planar, you also have this body contact, right? NMOS, you have NMOS body, PMOS, you have a PMOS body. Okay, so all right. Because we moved to the FinFET, so there are certain properties, that's actually a lot of things changes. So here are the things that I think it will really impact on your analog circuit design. Okay, so those are very good summary. Okay, very good summary of all this. So typically when they do this, they do fully depleted, right? So channel. So so all this show channel effect, will be less. Okay, so you have better control over the channel basically. And when you get to the FinFET, you would typically allow for lower supply voltage. Okay, and then a smaller energy switching energy. And you also have a less leakage power. Okay. This is because the gate, you have a better control. Right? I might have mentioned this in 536A. Okay. The good news is that you actually get higher GM and ion. Okay. Your current you can deliver per area. You will be higher. Okay, you will be higher. So that's actually good. So because all these are expensive, right? So with a given area, you can get more current or GM. That's always a good thing. You also have a less depot effect. I think I talked about this in 536A, right? So depot effect is when you have a drain voltage change. You will change your threshold voltage and all that. So all this will be less. Your body effect is also less. Okay, so that's also good news, right? So you have less variation, because of this second gate, right? The body gate changes. But just like anything, right? There's a good side, there's a bad side, right? So if let's say in the past you have been using this backgate biasing technique, I think I mentioned this in 536A, right? Sometimes people use a body gate to control your threshold voltage. So this big body biasing technique will be less effective, basically. Okay. All right. So there will be also less mismatch. So the variations still depends on the area and geometry, just like what I teach you today, right? So that inverse proportional to square root of the area, that generally is still true. Okay, so far they are kind of good. Of course, it also comes with a downside, right? So one of the downsides is that the channel width here is more quantized, right? Because now it all depends on the fin, number of fins, right? It's not like in the box CMOS, you can change the W, right? Pretty much arbitrarily, right? If you change W, any value, okay, 200 nanometers, oh, okay, no, I want a 205 nanometers, you can just do it. Okay. Right now, no, you have to do number of fins, so it's more quantized. The parasitics, this is a big thing. Okay, so if you start to work in FinFET, this is really, really huge. Starting from your drain and source, okay? Your drain and source resistance is much higher compared to CMOS, bulk CMOS, and also the coupling, you know, the CGS, CGD, you know, the coupling also become quite severe. Why? Because now you have a fin, right? Fin, you have the three sides, so you just provide more coupling paths over there. Okay, so those are actually a serious impact. And also because the way that you construct the fin, you know, you may be more prone to the latch up issues. Okay, so that's also something you need to be careful about. And self-heating. You think about all these devices, right? And then now they are, you know, in this vertical channel. If you have a heat, like a heater, you have a heat, you heat up the room, and your room is so tiny, what happens? You have the same heater, the room becomes so tiny, your temperature just go up. Okay, so all those temperature, you know, self-heating issues, you know, become a real concern. All right, so that's kind of what we are facing today, and I really like these slides. So this is provided by MediaTek. They did some study. Okay, so this is one of the big semiconductor company. As you can imagine, they have a lot of tape outs. And they do this in different technology. Now that I believe these are probably TSMC. So 28 nanometers is a bulk CMOS, right, or planar CMOS. On the right, when you get to TSMC 16 nanometer or 7 nanometers, then you are in the FinFET territory. You are absolutely in the FinFET territory. Okay, so let's go one by one. I think this is a very useful slide. You know, I think all of you can benefit from this. So first of all, your BDD, you see, does it go down? The supply. By the way, because they need to protect the foundry data, they don't show you the actual value, right? So everything is normalized, right? So let's say 28, they normalize to 1x, and they look at the others. Because nobody wants to go to jail, you know, and that including myself, right? So we cannot reveal the actual data. But it's normalized. It's 1x and 28, right? So here, now you are like 80% down. That's BDD. All right, off current. So this is kind of your leakage current, right? Look at this. This is actually one of the big reasons why people go for FinFET to begin with, right? Remember, all the technology advancement was dictated by the digital guy, right? I mentioned this before, right? And those leakage current will determine how leaky they are when they are in the sleep mode or idle mode, right? Look at this. This is what? Only 20% of the original. So this is what, 5x? 5 times difference, right? So this is one of the, obviously the big reason why people move to the FinFET. GM, right? Remember I said that a GM given area can go a little better. I think it's about what, 30-40% better, I would say. I know you do need to read yourself, okay, because they try to hide the data. R out, very good. R out, what is R out? The channel modulation effect, right? So how this drain voltage will modulate this threshold voltage, and you model that as the effective, channel length. So that effect is a lot less right now. So that's why you have a much higher R out. Okay, so this is actually very good. Actually, is that good? If I tell you R out of this device is high, is that good? Why is that good? Again, GMR, that's exactly right? Look at this, GM times R out. I think in total you have improved what? So it's 1.2, 1.3x times 5. It's pretty good. Very good, right? Remember I mentioned that, I think maybe last week or 2 weeks ago, most of the time, when you scale down, everything go bad. This is one of the special case where, oh wow, this is actually pretty good. VT, right? So threshold voltage, I said that before, you cannot go down too much. They still go down because you want to sustain the VDD lower, but your VT will, cannot go infinitely down. R on, so this is on resistance. Okay, when you turn on this, okay, so this also improve. The mismatch factors, also this also improves. So this is referred to more like ABT. You remember those A factors, ABT, A beta, A factors. So in general, it's go down by about 20 to 30%. Okay. So those are basically how those foundry like TSMC, they are selling to the whole world, right? They say, okay, yeah, you guys need to move to the FinFET because of this. Okay, so here is a summary of all this we just talked about. One thing, as you will see later, is that all this performance become better, if you consider only the fat, the most fat. However, there's still passive, right? Some passive parasitics. So it's mixed. Okay, so you're gonna see some pushback. Okay, so you win some, you lose some, right? So this is what I mentioned last week. It doesn't matter, in the future what technology nodes you are facing, you always have some property become better, some are gonna be worse. So you got to deal with it. Okay, so it's just a matter of you kind of need to understand the different trade-off. Then you can always survive, regardless of the technology. Okay. All right. So they are getting very difficult, and later on I will show you, what are the foundry people are going right now. And obviously this is a very hot area that everybody will try to get this as if this is national security, right? Okay. So this is on the sort of the pitch or the size, right? So you can see all these are scaling down, right? You can see from the 40 nanometers all the way to 7 nanometers. So the pitch, so this is spacing, okay, between the gate, go down, right? Go down. Pitch between the metal, so those are metal wires, go down. Once you get to the FinFET, right? So starting from 16, right? So between the fin to fin, there's also a pitch, right? Those pitch, they also go down. At 7 nanometers, if you look at the pitch, are they 7 nanometers? They are not, right? So that's where I mentioned before, they start to have some discontinuity, right? So there's a mismatch, basically, right? So even though you think that everything is 7 nanometers, no, it's not, right? So there's some actual numbers. But by and large, you see all this geometry, they scale down about 70% every 2 years. Every 2 years, they will scale down by about 70%. So, I mean, it's something, but it's not dramatic. I think that's Yeah, so I think this is summarized in all this, right? So the no name, is decoupled. Right now it's decoupled, right, to the actual area or the pitch or the length. The EUV machine obviously is one of the important equipment to make all this fine pitch processing. And the whole world is competing for this, right? You can, it's so sensitive, so they block us out. So right now, the whole world is competing for semiconductor, right? You guys know this, right? So everybody's competing for who can manufacture the best technology node, who can have the best yield, right? Who can have the best yield. So what they do? They compete. They control your source. What is your source? It's the equipment. So if you want to ban certain country or a certain region of the world that, okay, I don't think that they should produce advanced nodes, advanced chip, they cut this supply out, right? So they start to do even this fancy trade or what do they call it, restriction, right? So they will ban certain people or certain country to actually, acquire those equipment. So that's become a kind of beyond technology, right? Beyond technology. So even this political fight, they would start to restrict the access of technology, right? So, okay. So of course, people are trying to find a way out, to see whether they can even manufacture the chip without the EUV, things like that. So that's still an ongoing business fight. Okay, but don't worry, this is not a process class, so we'll just worry about the circuits. So in the next few slides, I will show you some of the design reality. Okay. In the FinFET, it turns out that they use a high-K metal gate material for the for the gate, right? So you cannot just arbitrarily increase the channel length. So there's an upper bound. Okay. But in the case that you say, hey, I do want to have a higher channel length. Okay. So what do you do? You put them in series, right? So I think I talked about this in 5368, right? So you put that in series. So effective channel length will just keep increasing. Okay, so that's no problem. However, if you plot this R out, okay, ideally speaking, you increase the effective channel length because you want to make R out even higher, right? You agree? Or you forgot? 5368, right? But then if you plot this R out over frequency, what you're going to find is that all this, you have parasitic capacitance, right? So unfortunately, unless you are a low frequency current, you see your current will go through, will flow from drain to source, and all the way down. If you have a high frequency current coming in, you start to see this capacitor. So some of the current, they don't flow all the way down, right? They get intercepted. In the middle, they shunted to the ground. Okay. So what that means is that if you look at the AC resistance, right, the R out, at the high frequency, you're gonna start to see the blow off. Okay, you're gonna see a lower output resistance. Okay. So basically there is some trade-off that you can do. Whether you should use a larger L or minimum L to do the stacking, right? Because if you do minimum L, then you need more stacks. If you have a larger L, then you have less stack, right? But you know, different L, they also have a different parasitic capacitance. You see, even this at this level, it becomes a trade-off. Even at device level, you start to ask yourself, oh yeah, so how should I choose this and how many stacks should I do? Even on the one transistor level, this become a design. Right? In the past, you know, okay, so in circuit design, maybe it's, oh yeah, this is more like a distributed, you know, transmission line effect, or this, you take BOSI class, it's more like Elmore delay, that kind of, more like a system level, you know, routing issues. And now all of a sudden it become, even on the single device level, you see the circuit. Right? So trust me, all the circuit analysis design is even more important right now in FinFET. Okay, so there are a lot more bullet points, so I will give you this slides so you can use that as your reference for the futures. Thick oxide, right? So in the bulk CMOS, you know, we do have a thick oxide, and so is FinFET. Okay, and one of the good reason is that, you know, even for the FinFET, you know, even though your supply voltage keep going down, right, sub 1 volt, but your FinFET circuits, you still need to talk to outside people, right? Outside chip, maybe a microprocessor. So this is what we call the general purpose I/O. So you have a GPIO, that's how we usually call it. When you talk to outside people, you got to talk to legacy chips. Does that make sense? Right? So maybe I'm getting this a TI chip, you know, maybe using 180, right? My chip still need to talk to that, right? So you still need to use sort of this higher voltage, you know, supply. So unfortunately, we still need the thick oxide I/O. Usually, the thicker oxide I/Os, the thick oxide device, they can sustain higher voltage. Okay, so thicker gate oxide, because you know you won't break down as easy, so you can sustain higher supply voltage. Okay, so for FinFET, what's the problem if I make a thick gate oxide? In the planar CMOS, where is this gate oxide? It's planar, right? So the gate here, underneath the channel, you just go up. You go up, right? Go up. In FinFET, if I say that, okay, please make the gate oxide 5 times thicker, what happens? You can squeeze even horizontally, right? So you see, so there are constraints. You know, it's not like, you know, in the planar CMOS, okay, just go up. You know, here, no, you even would affect, you know, your neighbors. So how do you, you know, the fin-to-fin spacing? How do you do that, right? And can you even process? Because you see, you need to deposit the metal gate here, so it becomes very complicated manufacture process issue, basically, right? So yeah, so I think you see all this, you know, a lot of these are processing steps. You see, you know, when you have a tight fin pitch, you know, it's really hard to fill in all this metal gate, right? Because you have a thicker oxide right now. So yeah, so all those present really complicated challenges. Passives. So in the old days, in the planar CMOS, the gate usually we use a poly gate, polysilicon. Okay. So in fact, a lot of times, you know, in those technology nodes, whenever we do the resistor, we will use a poly resistor. That's how we call it. So we basically use a poly gate, city side versus on-city side. So they give you different resistance. Okay. So that's usually how we do the resistors. Turns out that, you know, in the FinFET, right? So because now it's moved to the metal gate, so it's harder to actually have this really high precision resistor. Okay, in the city side, the poly gate, they can control it better. This one is just more difficult, right? So just keep in mind, yes, you know, there's gonna be a metal gate resistor, but you're gonna end up with more variation. Okay. So that's something that we actually do need to deal with. The capacitors, there's still a mount cap. Remember mount cap, finger capacitor, right? There's still a bin cap. Okay, so the capacitor you can still, have it, and just because all this metal pitch is closer, so you still enjoy the higher density. Remember I showed you the plots, different nodes, so that's still good. Okay, so some still good, some not as good. Yeah. And then you still have a diode and bipolars, but all these resistance also become higher, so I think they also face some challenge on those bipolar and diodes. Interconnect resistance, okay, because everything shrink so much, right? Your transistors shrink so much, so of course your routing metal you should also shrink, right? Does that make sense? I mean, you cannot say that, oh, all the transistor right now is 10 times smaller and my metal is still as wide. How do you reach to that particular transistor, right? So you can see the cross section, right? For the copper, that's usually the material that we use. It's just much smaller. Okay, so if I say that if this metal wire cross section is smaller, that means resistance goes up, right? So cross section smaller, right? So that certainly is what we are seeing. So you're seeing this MX is the particular metal layer, right? So M1, M2, M something, right? Resistance, you can see the scaling 16, 7, 5 goes up. You see that? 28 to 16, maybe just go up by how many X? 1 point something X, right? But you see from 16 to 7 increase by 3X, and then from 7 to 5 increase another 3X. Okay. So resistance is certainly one of the big things that you need to consider, right? So all this routing, huge issue. Capacitance, turns out that the capacitance, does not increase. I mean, still increase, but it is not as bad as resistance. So it turns out that in the FinFET design, the IR drop, right? So every time you think about how you connect your transistor to the next, all that connections, you almost should think about, okay, as if I'm adding a resistor. Okay, it's almost to another level, right? It's not like in the planar CMOS, we thought, oh, what do you mean? Just put the metal and short over. So that's kind of the reality that we are facing. Okay, so if you zoom into the single device, the gate resistance also increases. Okay, because everything, again, still because your cross section becomes so small, right? So all this gate resistance, when you distribute to here, you need to start consider all this R effect. Even though you may think, hey, all those 4 fins, they show together to the same gate. Okay, but it's not really. You see all this resistor, right? So you reach to the first fin, second, third, fourth. From here to here, the last fin will see the higher gate resistance. Okay, you almost should think about this as 4 different transistors. Almost. Okay. All right. So that kind of become interesting consideration. Gate to contact capacitance, I mentioned this a little bit, right? Before, your CGD, CGS, because now you have a 3 side. Those coupling capacitance become a lot bigger. Okay, so, and this is for sure is real. A few years ago, when my students are working on this, and they start to report that, hey, no, this bandwidth set by this gate of that transistors becomes so low. And I was like, how is it possible? Everything scale up, speed should improve. Why is it that your pole frequency here become lower? Then we start to realize, oh, because you do FinFET. Okay, you do FinFET, you have all this 3 side coupling, right? from the gate to the drain and source. So you see the CGS or CGD will increase. Then the question to you is that, what happens if the CGS and CGD increase? It depends. Depends on your circuits, right? Different scenarios. So for example, in the LDO design, here the power rejection ratio will be worse. Remember I asked you this question in 536A? Is it midterm or final? So one of those, I think I might have asked you this power supply rejection ratios. Kickback noise, because your CGS is larger, right? So here, can also increase. Okay, so there's basically a lot of design consideration just because of the CGS and CGD is larger, and it will also affect your startup time. So just something to think about. Flicker noise. Unfortunately, the flicker noise appears to be worse. Okay, compared to the planar CMOS. Look at this. PMOS about 7 times worse. A MOS is about 1.1x worse for the flicker noise. Okay. So you just need to think about what happens if your flicker noise indeed is higher. So by the way, everything that you learned in the 536A is still valid. Okay, still if you size up, your flicker noise will still go down. That one's still true. Okay, still true. It's just that you probably need to do harder to actually reduce to the same level. Okay, so one thing about the FinFET is that because you make everything so small, it becomes much more layout dependent. This is why this tape-out class becomes so important. Okay, I don't think we can allow you to do FinFET in the layout class. It's way too expensive. Okay, even if you want to increase your tuition, there's no way. Okay, but in the future, if you're gonna do the FinFET layout, right? This is where you really have to face, right? So, we talk about LOD effect, right? So all this OD, the distance, right? The edge, to the edge of the drain and source, for sure it will affect. The gate pitch here will affect. The width of this will affect. Everything will affect. And by the way, it's not just you yourself will affect yourself, okay? It's to your neighbor. You have a neighboring device right here, right? What is spacing? What is spacing between that? It will all cause this, mechanical stress, and different stress will affect, mobility, threshold voltage. Everything is tight. So what do you do? Right? So what do you do? Yeah. So later on I'm gonna show you some tips, right? So this is really the reality. Okay. So one can argue that in the FinFET design, if you don't reach to the layout scale, everything you talk about is a joke. So this is how serious it is. So this is what people already say. Okay. So yeah, without you doing the layout extract, show us the simulation actually works. I'm not going to believe you at all. It's more like just a class homework. You do it, okay. You don't know, you don't know, you don't test it, you don't know. Okay. The gate cut, right? So everything, is in the FinFET will be more in the regular pattern. So you see this is a gate, this is a fin, right? So what they do, because right now it's so tight, the foundry cannot just say that, oh, okay, so you need a gate here, let me do a gate here. They don't do this. When they do the manufacture, they do all this like a grid, right? You see the entire wafer here, they just, all these are the gate. All these are the fins. In the event that you say, hey, no, this transistor and that transistor are different transistors, what do? They remove it. They cut it. Okay, so that's how they do. They put it, It depends. Oh, you don't want this? You want this to be connected? Oh, disconnect? Okay, let me just cut it out. Okay. As you start to do this so-called gate cut, so this is a 3D view, right? So you see all these cuts, so going down, gate cut. You're gonna cause some stress. Again, it's a stress. It's like you have a wall here, and all of a sudden, this wall, there's a gap. So it causes different stress level. You change the property again, right? So look at this. So this certainly will see a different thing as here, right? So everything become not just electrical design, it's a mechanical design because it's so tight. Everything is so tight and everything is so sensitive. Okay. Similar thing, right? So how you route the metal, you do continuous or you disconnect, it will affect all the property, right? Density, by the way, you are going to see in the FinFET, the density of your transistor, your metal, affect everything. Okay, so when you take the tape-out class, you're gonna see there's something called the density dummy fields. Have you heard about this? They do dummy field and to get the density roughly the same. In the FinFET, it's even more important. Okay, so in the past, usually what they do, so if you take tape-out class, you're gonna do this exercise. So they have this window. So they have this window. They will say, okay, within this window of area, what's your density? They need to make sure your density, let's say between 20% to 40%, let's say. Okay, and then you slide the window and you check again. In FinFET, it's a lot more stringent. Okay, you no longer have a luxury of, oh yeah, let me just draw a big window and then just make sure that it's all fitting with that density. This, they do a lot more rigorous check for that reason. Okay, so what really that means is that you got to do a lot of floor planning. So when you do the FinFET design, if you don't bother to do floor planning in the beginning, the whole project is a joke. You don't need to continue. The whole project, is not gonna succeed at all. You have no floor planning. You don't know where you're gonna place all these transistor or capacitors. Okay, forget about it. Even if you are so good, okay, I can write this KC or KBO. I know this phase margin. I know how to. Okay, good luck. Okay, you're still gonna fail. Okay, you're still gonna fail. Okay, so so all this really just almost like a nightmare, right? And then you're gonna run into tons and tons of DRC errors. Remember we talked about DRC last time, right? The DRC rule, a lot more complicated than the planar. Okay, it's just way more complicated, right? So usually when you get to the FinFET design, you just need to leave more time for the layout. You're gonna fail, you're gonna fix it. Even after you fix it, you do the simulation again, completely different from your schematic.
Are these not automated? Like,
Yeah, you wish, yeah. And by the way, so for the digital, they automate a lot more. The digital, so all they comes down to is that, all those tools, they're gonna impose more and more constraints. So when they do the floor planning, place and route, they do the job for you. Unfortunately for analog, because you do things manually. You just need to know. You need to understand all these rules, and then you just need to follow it. Okay. Don't worry. I've the slide. I will give you some guidelines. Yes.
What do you mean by transition?
Oh,
Like the
no.
yellow.
Yeah. So this is a transition between these basically different blocks, right? So all these are synthesized. So you can see it's more like spaghetti. So the tool will do all this. So they have their own density, and this is a custom digital. So they have a different density. So you have some transition area. So let's say you have some gradient for the density, and another good reason to have some transition layers gaps there is you can shield the noise. So you have some guarding and things like that. Okay. And sometimes the transition is will be enforced by the DRC rules. Okay, so they will do that. Remember before I talked about IO device, thick gate oxide. So you cannot just go there and just, oh, by the way, I want to put a thick oxide device right here, and then a thin oxide next to it. The foundry cannot just allow you to do that, right? It's, oh, do one thick oxide here, thin oxide here, and two more thick oxide and one thin oxide. Good luck with that, right? You're gonna cause a lot of DRC rules, a violation. They will say that, oh, most likely they will say, okay, space out. Okay, if you want to claim this area as a thick oxide, it's okay. Just put everything here as thick oxide. All right, and then you have some transition, so you space out. And you say, okay, starting from next room, you're gonna do the thin oxide. So you can do this. Okay, so here is more processing, so I will skip all this. So basically, just different processing steps. You know, it will cause the variation. The etching. So this basically just tell you, you know, why there's a lot of variation for all those devices. And some will be related to the density, you know, how dense you are, right? You know, or less dense, you know, it will cause different property, right? So like CMP, you know, this is also the processing step, you know, how you do a CMP, you know, it will cause different level of the effect. Okay, so these are the typical models, right? So so the foundry they try very hard to capture, you know, fat or metal. So they characterize all this, you know, in the foundry. They do a lot of tape outs. They characterize this. They back calculate, you know, all these parameters. So supposedly all this, you know, the foundry they are trying very hard, you know, to bring in this gap. Okay, to bring the gap, you know, between our simulation, which is basically using the model, versus the real silicon. Okay, so they do this a lot of back and forth. You know, the front end, like MOSFET, the metal, which is the BEOL models, reliability. Remember I talked about the etching effect? Remember etching effect? They still model it. Okay, so all those FinFET, you know, HCI, you know, BTI. Remember I talked about this MBTI and PBTI, right? So they usually would do that, and TDP and electro migration. So they do all that. Right now, I think there's no secret. All these foundry, they are fighting with each other to the point where the whole country is involved in the fight. They become so paranoid, they don't tell you what's the real number. So today, it's different from old days. Old days, if I look at the PDK, that's why you see, if you work with the real foundry, they must ask you to sign an NDA, right? You cannot disclose any information. If I disclose the PDK information, I release the information that the foundry is doing. Oh, I look at this, I know what's the gate length. I know what's the pitch. Right now, even if you have the PDK, you still don't know. Everything becomes so sensitive right now. By the way, you still need to sign an NDA. You still need to go to the jail if you break that NDA. You still need to do all that. Even if you accidentally leak that information, they are so sophisticated, they don't give you the information. Okay, so you look at those PDK models, they are encrypted. You don't even know. Okay, and not just that. You know, in the past, you know, actually not even in the past, even in the 536A, right? So you how do you change the size of the transistor? You change the W and L, right? Even if you enter that L, it's not a real L. You think, oh, I do 40 nanometer, but it's not. What's the exact number? I don't know. You don't know. Okay, but whatever that you enter, it's almost like a lookup table, right? So you enter something, there's this real lookup table, and then we'll find out what's the real behavior of that device. Okay. So it's no longer the case where you can just tell their competitor, oh, by the way, I tell you a secret. You know, I was so fortunate. I work on this advanced node. I have this number. That's what I enter. It means nothing, right? So they become very sensitive and become very sophisticated. Okay. You know what? How about this? Let's take a short break, and then we'll continue, and hopefully I'll finish the rest.